This video covers Lecture 2, Basic Statistical Concepts. We'll talk about the basic concepts in probability and statistics, including statistical models, statistical inference, check normality assumption. We'll introduce simple comparative experiments, the hypothesis testing framework, and the two-sample t-test. And some other topics include how to determine sample size and randomization test, paired comparison design. First, let's look at some basic concepts. Population sample. Population is the entire group of individuals in which we're interested, but usually cannot assess directly. Sample is the part of the population we actually examine and for which we have data. Now, an example of population would be A&T students or trees in America. A sample would be 30 A&T students randomly selected. A parameter is a number describing a characteristic of the population. Parameters are usually unknown. We usually assume that a population follows a certain distribution that depends on some unknown parameters. The parameters can be mean, standard deviation, and so on and so forth. A statistic is a number describing a characteristic of the sample. We often use a statistic to estimate an unknown parameter. So, population mean could be a parameter, and a sample mean would be a statistic. The random samples. A random sample usually is written as X is a variable whose possible values are numerical outcomes of a random phenomenon. In general, there are two types of random variables, a discrete and a continuous. Discrete random variables. A discrete random variable X has a probability mass function, which can be defined as this. Summation f of x will be equal to 1, and little f of x is a non-negative value. Its mean measures the center of location, and its variance measure the variability or dispersion. Examples of discrete random variables include the number of children in the family, number of defective items in a box, and examples of continuous random variable could be height and weight. Continuous random variables. In general, a continuous random variable y can have values from an interval, and its probability function is called probability density function, and usually we use the integration to calculate for a probability related to a continuous random variable. Let's look at some useful formulas. Suppose x and y are two random variables, little a and b are two constants. Then the expected value of a times x plus b times y is equal to a times e of x plus b times e of y. And we also have some other formulas that can be used. And you can refer to the textbook for other formulas. Normal distribution is one of the most important distributions in statistics. We can use normal distribution to calculate the probability of getting observations greater than or less than any value. Usually we can calculate the area under the curve, and as you can see, a normal distribution curve is bell-shaped and symmetric about the mean. And we have its probability density function and its mean and its variance. From the two graphs in the bottom, you can tell even if the two distributions have the same shape, if the locations are different, they're different. On the other hand, even if the center of the location is the same, these three distributions vary in terms of their shape. All normal distributions are symmetric and have bell-shaped density curves with a single peak. All normal density curves satisfy the following property, which is often referred to as the empirical rule. Roughly 68% of the observations fall within one standard deviation of the mean, 95% of the observations fall within two standard deviations of the mean, and 99.7% of the observations fall within three standard deviations of the mean. Therefore, for a normal distribution, almost all values lie within three standard deviations of the mean. Let's look at the statistical inference. The objective of statistical inference includes point estimation, confidence interval, and hypothesis testing. Statistical inference is based on the laws of probability and allows us to infer conclusions about a given population based on results observed through random sampling. We typically also need to check model assumptions when we make a statistical inference. Let's look at point estimation of parameters. Population parameters are estimated by their sample counterparts. For example, population mean can be estimated by sample mean. Population variance can be estimated by sample variance. So typically you try to get a sample from a population, and then you make an inference about the parameter of the population. Note that each observation in a random sample is a representative of unobserved variables in the population. The question is, how different would this observation be if we took a different random sample? So here this graph shows you from the population, you do sampling, you get samples, and you can get some estimation. Therefore, you can calculate the statistic about the sample. From statistic, you can make an inference about the parameter of the population. So for instance, we can use sample mean y bar to estimate the population mean mu, and we use sample variance s squared to estimate the variance, population variance sigma squared. In point estimation, when we talk about the specific value of the statistic, we use the term estimate. And when we talk in general about the statistic, we use the term estimator. So, from the previous slide, we know what we would do is take samples from the population, and for each sample you can calculate a sample mean, and those sample means might be different across different samples, and we're going to use the average of those sample means to do the estimation for the unknown parameter mu. But it would be interesting to see how the distribution of these sample means look like. Sample mean is our estimate of population mean. Over repeated samples, the sample mean will, on average, be equal to the population mean, but there is no guarantee for any one sample. How much would the sample mean change if we took a different sample? The key to the question will be the sampling distribution. So, a sampling distribution is the distribution of a statistic. When we repeatedly draw a sample of a size of n is equal to 30 from the population, the means follow a distribution. So for instance, the first sample we draw from the population with 30 data points, we get an average 77.83. The second sample, we get 80.25, and so on and so forth. And then when we plug all these numbers, we get a histogram of the sample mean. Because let's say y1, y2, and yn are independently sampled from a normal population with mean mu and standard deviation sigma, the average of average will be the mean of the sample mean will be calculated as E of y bar is equal to mu, and when we compute for the variance of y bar, we get sigma squared over little n. In fact, we also know that y bar follows a normal distribution with mu as the mean and sigma squared over n as the variance. Notice as sample size increases, the variances of the sample mean decreases because of the sigma squared over n. This indicates that averaging over many observations is more accurate than just looking at one or two observations. Here we can compare the sampling distribution of the sample mean when sample size is 1 versus sample size is 10. Now, the law of large numbers tells us if one draws independent samples from a population with mean mu, then as the number of observations increase, the sample mean x gets closer and closer to the population mean mu. When sample size n approaches infinity, the variance of sample mean approaches 0, and the mean of the sample mean is the population mean. If our data x1, x2 up to xn follow a normal distribution, then the sample mean x bar will also follow a normal distribution. This is true regardless of the sample size. Now, what if the original data doesn't follow a normal distribution? This is where the central limit theorem comes into play. Central limit theorem tells us when randomly sampling from any population with mu as the mean and the sigma as the standard deviation, if n is large enough, the sampling distribution of x bar is approximately normal, and its mean will be mu and its variance will be sigma squared over n. This is true no matter what the shape of the distribution of the original data. When a variable is normally distributed, the sampling distribution of the mean is exactly normally distributed. The sample mean is an unbiased estimate of the population mean. Recall that E of y bar is equal to mu. The sample mean is less variable than individual observations because the variance of y bar is equal to sigma squared over little n. The mean of the sample mean is equal to the population mean, and the variance of the sample mean is equal to population variance over the sample size.